So we're back at the motel, folks, and this is our chance to put our understanding of entropy from Bobby into perspective. So let's sum up what we learned and say that entropy increases as systems naturally transition to states with more energy and greater particle arrangement possibilities. Or simply, an increase in entropy is an increase in the microstate number. And this increase in entropy or microstate number often guides the direction of spontaneous change. And we also said that if delta S of the system is positive or greater than 0, then we're going to have an increase in entropy and it's going to favor spontaneous change. And if delta S of the system is less than 0 or negative, then we're going to have a decrease in entropy, and that's going to favor non-spontaneous or less favorable processes. But we also said our understanding is not the full story. And the question remains, why, right? We'll learn details about the other contributing factors as the hunt continues. But for now, it's as simple as we must consider more than just the entropy change of the system. Again, our understanding thus far has been about the system, but focusing solely on the system might lead us to overlook the influence of the surroundings, which of course can impact the overall understanding of spontaneous processes. After all, at 20 degrees Celsius, solid water melts spontaneously and the delta S of the system increases. And at negative 10 degrees Celsius, liquid water is going to freeze spontaneously and delta S of the system is going to be decreased. Therefore, simply looking at the sign of delta S of the system, and the system for us is a reaction, right, does not predict the direction of a spontaneous change. So we must consider the system and its surroundings. If we consider both the system and the surroundings in our understanding, we find that all real processes are going to occur spontaneously in the direction that increases the entropy of the universe, which is a definition of the second law of thermodynamics, folks. And we can actually quantify the second law for any real spontaneous process with the expression delta S of the universe, which is a change in entropy of the universe, is equal to the sum of delta S of the system, our system is a reaction, plus delta S of the surroundings. And this combined value must be greater than 0 or positive to ensure the spontaneity of a process according to the second law of thermodynamics. For example, for a process to be spontaneous, a decrease in the entropy of the system must be offset by a larger increase in the entropy of the surroundings so that we remain positive and greater than 0. And of course, we can look at the vice versa. If we have a decrease in the surroundings, we want to make sure that we compensate with a larger increase in the system. So again, that we remain larger than 0 or a positive value. With this knowledge, we can firmly say that the entropy of the universe ensures spontaneity. How does it ensure spontaneity? By increasing and of course remaining positive or greater than 0. And by looking at the delta S of the universe value, we can verify spontaneity based on if the value is greater than 0 or less than 0. So while delta S of the universe is going to help us determine spontaneity, predicting the full range of spontaneous changes will require further research as we continue the hunt. Nevertheless, the discussions on entropy with Bobby and the second law of thermodynamics are still crucial for understanding and determining spontaneity. And we're going to be using the same information later on in the lecture. And of course, without these explanations, we wouldn't be able to predict spontaneous changes accurately. So the investigation continues. So we just discussed how important it is to understand delta S of the universe for spontaneous changes, right? And we will continue that conversation soon. But we must double back and go deeper into learning about entropy of the system. Like, what happens to entropy when the system only has one microstate and is at 0 Kelvin? A discussion that's not about spontaneous change, but one that will help us understand entropy in its standard molar state, learn a new thermodynamic law, the third law of thermodynamics, and provide a reference point for entropy calculations. All of this so we can get back on the hunt for spontaneous change. To get oriented, we use state functions to comprehend the behavior and changes within the system. And of course, state functions mean we focus on the final and initial states. I chose enthalpy and of course entropy. And although entropy and enthalpy are state functions, their values differ in a fundamental way. For enthalpy, there is no 0 point. All we can do is measure only changes in the amount of heat absorbed or released in each reaction, or simply the changes in delta H. But with entropy, Nobel Peace Prize winning chemist Walter Nernst found that there is a 0 point, and that's at absolute zero or at 0 Kelvin. And if there's a 0 point, we can determine absolute values, meaning we can obtain the actual numerical values of entropy versus just measuring changes or differences. So the question becomes, how? Well, Walter Nernst, he actually formulated the third law of thermodynamics, which states that entropy of a perfect crystal is 0 at absolute zero or 0 Kelvin. And we can quantify this expression by saying S of the system is equal to 0 at 0 Kelvin. And a perfect crystal, like we see here, simply just means that all the particles are aligned and they have minimum energy and there's only one microstate. So with one microstate, we can use the Boltzmann equation to solve for S of the system. And that is how we get our 0 here. So I want to plug in the 1 microstate value for our Boltzmann equation. That's going to be S is equal to K natural log of W. Our W here is equal to 1. Natural log of 1 is equal to 0. If you multiply 0 by K, it's still going to be 0. And this is how we get S is equal to 0 for our system at 0 Kelvin. And this, of course, is going to prove that at absolute zero with 1 microstate, S is equal to 0, exactly like Walter Nernst said. Now that S is at 0, we can calculate delta S using one of the ways Bobby taught us. So we're going to use a reversible process and calculate delta S of the system as Q reverse divided by T. And we know from the third law that delta S of the system is going to equal to 0 at 0 Kelvin. So at 0 Kelvin, we're going to have this perfect crystal. And if we warm or heat up this perfect crystal to any temperature above 0 Kelvin, then the total energy increases. And that total energy is going to want to be dispersed. And it usually is going to be dispersed into more than one microstate. So as you can see, we have a lot of movement going on. We have an increase in energy, and that's going to increase our microstates. So our microstates is going to go from 1 to a number that's greater than 1. Our entropy is going to equal 0 here to a number that's greater than 0. So it's going to be positive or increasing. And our temperature is going to go from 0 Kelvin to a temperature that's higher than, of course, 0 Kelvin. Thus, an increase in temperature is going to increase kinetic energy, which is going to increase microstate number, which is then going to increase entropy. And we can also look at this and say, well, if our microstate number is greater than 1, and we use the Boltzmann equation, the natural log of a number that's greater than 1 is going to be greater than 0. And then, of course, if our natural log of W is greater than 0, then, of course, our entropy is going to be greater than 0 when our perfect crystal is heated up. Therefore, to find S of a substance at a given temperature, say for 298 Kelvin for us, we're going to get that substance as close to 0 Kelvin as possible. Then we're going to heat the substance up in small increments. And as we heat it up, we're going to take our Q reverse and divide it by T, and therefore get our delta S of the system volume. And we're going to keep increasing, keep dividing Q by T, and keep getting our delta S of the system value all the way up into the temperature of interest, which is 298 Kelvin. Then all we need to do is sum up all of these entropy increases from 0 Kelvin up to 298 Kelvin and integrate over the entire temperature range using calculus to obtain the absolute entropy value, or to obtain S, and specifically to obtain S at 298 Kelvin. Being able to get the S values for several substances at 298 Kelvin is useful for us in chemistry. In thermodynamics, we will compare entropy values at 298 Kelvin in standard states. So we have to remember what a standard state is. A standard state means that we're going to be, of course, at 298 Kelvin. We're going to be at 1 atmosphere for gases, 1 molarity for solutions, and the pure substance that we're using must be in its most stable form for solids and liquids. So now when we discuss entropy, you will now see the degree symbol or the not symbol, and that's going to verify that we are in the standard state. Now we must layer a little bit of information here. We saw that entropy tends to increase beyond the amount you start with as we increase the number of microstates, right? Therefore, entropy is an extensive property, and that isn't one that's going to depend on the amount of substance that you have. So when we're going to go get our units for our entropy in the standard state, we must specify entropy as the standard molar entropy. So the standard molar entropy of a substance is measured for a substance in its standard state in the units of joules per mole Kelvin at 298 Kelvin. Okay, folks? Again, when we have our regular old entropy we've been talking about, our units have been joule Kelvin. Even when we have our delta S, it's been joule Kelvin. When we're talking about entropy in the standard state, we now are going to be joule per mole Kelvin. Even if we're going to be talking about in the future, delta S in the standard state, you will have the units of joules per mole Kelvin. I will tell you that as we go along in calculations, you will see a lot of times that we have our entropy as just simply joules per Kelvin because we usually are talking about 1 mole of a substance, right? And if you do have more than 1 mole of a substance, you will just take your entropy value and divide it by the number of moles. Again, we are usually dealing with 1 mole, so that's the reason why we simply just get rid of that 1 or dividing by 1 and just have the units as joules per Kelvin. And you'll see these examples as we go along. Let's look at some standard entropy values at 298 Kelvin for some substances. And of course, all these substances here are a mixture of elements, compounds, ions. And we have a Br2 as gaseous form, has a standard entropy value at 298 Kelvin at 245.38 joules per mole Kelvin. But in the liquid form, it's 152.23 joules per mole Kelvin. And that makes sense because when you're going from a liquid to a gaseous state, you are increasing the number of microstates, so that you should have an increase in the number of your entropy value, right? Same thing if you're going from your gaseous state down to aqueous for our CO2 here. You're going from, say, 213.7 joules per mole Kelvin down to 121 joules per mole Kelvin when it's in the aqueous form. And so that's just going to be some examples here. Next, we learn about several parameters that affect the standard molar entropy of a system, or S naught of a system, okay? By knowing parameters that can affect S naught here, we can use this information to help us understand entropy better, and therefore understand spontaneous change and the direction of the increase of microstates better, okay? Sam and Dean think we have enough to go out and question initial victims of some of the phenomenon happening in Mystic Falls. So let's get to it, folks.